all of you. Welcome to the 28th lecture on the course on analysis and modeling in chemical engineering. In this week, we are talking about heat equations. In the first lecture in this week, we derived the heat equation, and in the last lecture, we have discussed a simplified version of heat equations in one dimensions for the case of heat transfer from a slab. So, I will talk more about that example in today's lecture, and then we will take some other example again for one dimensional heat equations. So, this is a quick recap of what we have been discussing. So, we started with a slab that is at the beginning at some temperature T naught, which can be much hotter than the ambient temperature TA or much cooler, but just for the sake of saying, let us say it is hotter to begin with. The answer or everything will not change if it is the other way around. So, we defined a dimensionless temperature, that is T cap, and we defined it something like T cap as T minus TA by T naught minus TA, so that it always starts from 1 at time t equal to 0 and goes to 0 at infinite time. And then we have derived for this case this series solution where this coefficients an comes from the initial conditions, right? And that initial condition is my T cap is equal to 1 to begin with. Right? This lambda n, they are having multiple solutions. They are coming by solution from this equation where we get multiple solutions. I did not consider the negative ones because T cap is an even function in lambda n, and whatever the factor that we have as a result can be included in this coefficients an. And we have already figured out there is a time scale tau in the problem that contains all the variables important in the problem, and I use that time scale to define dimensionless time T cap as T by tau, and there is another dimensionless variable here, the Biot number HL by K. So, let me now try to see, without solving this equation, can we get some insights into what can be possible, right? So, of course, we can numerically solve it, but can we get some insight without solving it completely, right? And one of the ways to get that insight is to approximate the series form as only the first term, right? So, there are two possibilities that every subsequent term is bigger than the previous term, then this temperature will anyway diverge. But if it is converging, that means subsequent terms are smaller than the previous term, then first term is going to be kind of dominant than the other terms. It's not that we can ignore all the subsequent term, but we can still approximate this T cap in the 0th approximation. Just to get some idea about the behavior of a solution, we can apply this kind of approximation to consider only the first term, right? And since the T cap is bounded, it is going from 1 to 0. So, there is good reason to imagine that this is going to be a converging series. As a result, the 0th approximation, that is considering only the first term, does make sense, right? So, if I only consider the first term, then the solution looks something like this. And now this lambda naught, again we can solve for that by solving this equation, and it depends on the Biot number. But then if I want to get some kind of a scaling estimate of the lambda naught, then from here we know that the lambda naught is in the range of 0 to pi by 2. So, I can say the lambda naught scales as pi by 2. I mean, not very accurate, but think about it, right? So, it is in the range 0 to pi by 2. So, I mean, that already set some kind of a scale, 20 pi by 4, pi by 6 something, pi by 2 is still something like 1.57. So, it is between this range 0 to 1.57. So, as a first approximation, we can imagine that lambda naught scales as pi by 2, right? It just sets an order of magnitude, nothing more. It is not the actual value, just the order of magnitude. And this cos lambda naught z cap, we can take it equal to 1 because z cap goes from 0 to 1. Let us set z cap to be 1. In any case, the cos lambda z is varying from 0 to 1 in magnitude terms, right? Let us set it equal to 1 just to get a rough estimate of how this temperature is varying with the time, right? And if I do all that, then I get something like this. From zeroth approximation, considering lambda naught scaling, I get something like this. That is, my t cap is changing with the time, the dimensionless time, by this kind of a relation. And if I then plot it, then we get a plot like this. And it tells me as a rough measure of how much time does it take to reach steady state. And what's the steady state of this problem? I mean, if you think about it, after a long time, the temperature is going to vanish. We are talking about T cap here versus small t cap, right? Temperature is going to vanish because the T will be equal to the ambient temperature. The T cap is defined as T minus Ta by T naught minus Ta, right? So when T is equal to Ta, then T cap goes to 0, and that happens something of the order of, let's say, 2. T cap is equal to 2, right? Roughly speaking, this T going to tau, that is when my T cap approaches 1, that is something like exponential of minus pi square by 4. If I plug in that value here, I get something like 0.084, that is fairly small, close to like 0.1, let us say, right? So the temperature has already dropped to 0.1 in the time of the order of the time scale tau. So the time scale therefore gives me some measure of the approach to the steady state. It is some kind of a time scale that is giving me a measure of the approach of the steady state or the final state of the system. All right. I could have got that without even solving the equation. So this estimate I have did without solving, but we did have the analytical solution available with us, and then we take the zeroth order approximation. Let us say I don't want to work with this analytical solution, or I don't have it. Can I get it simply from looking at the partial differential equation? The answer is yes, because we already know from this equation that my capital T cap, the temperature is in the range of 0 to 1. This Z cap is also in the range of 0 to 1, and therefore this T cap also has to be in the range of 0 to 1, and only then this is going to be comparable, right? So the first term is going to be comparable to the second one only when this small t cap is in the range of 0 to 1. If that is not true, let us say if small t cap is equal to 10, then anyway the first term is very, very small, and therefore we can ignore the time dependency that is happening at longer times anyway, right? So at longer times the time dependency is gone, and that would mean that this value is much bigger than 1. T cap is much bigger than 1, but they are comparable when this T cap is in the range of the order of 1. So when T is of the order of tau. So that tau basically sets the time that is required to achieve some kind of a steady state, some kind of the meaning of time constant for first order system, something similar we are getting here of the order of this time. You can imagine that you will start approaching the steady state, right? And we derive this conclusion without actually solving the equation, just looking at this partial differential equation. We just see when they are going to be comparable. Since every other term is outer order of magnitude 1, so this small t cap should be of the order of magnitude 1 in order for them to be comparable. The left should be comparable to y, and only on that basis we can say that my time should be of the order time scale in order to have some kind of an idea what time after this we will have the steady state behavior. Anything less than that, we can imagine that we will not have steady state. The t cap will be much bigger. The capital T cap will be much bigger. Now, we can also derive some conclusions about this Biot number. So, Biot number is my HL by K, and you can see where it came from originally. It was the boundary condition that gave it. What the boundary condition said, that the conductive flux from the inside of the slab to the surface, top surface, is equal to the convective flux going from surface to the ambient, right? So I equated those two, and I basically have got that. And the conductive flux, if I have to approximate, I can approximate as something like this. Let us say T0 is the temperature at the center line and TL is the temperature at the surface. Then to a first approximation, this T naught minus TL, the temperature difference, divided by the length L, this is some estimate of the temperature gradient dou T by dou Z, some kind of a linear estimate or approximation of this gradient dou T by dou Z. So now if I equate now the fluxes again, keeping in mind this approximation for dou T by dou Z, I will get the expression of the Biot number HL by K as something that scales as TL minus T naught divided by TL minus TA, that is the temperature difference from the top to the center line in the slab, that is my internal temperature difference, divided by the temperature difference of the top and the ambient, the top surface and the ambient, that is some kind of an external temperature difference. So the ratio of the internal to external temperature difference, that gives me the Biot number. And what do they depend on? The internal temperature difference depends on the K and the external ones depend on the H. If K is bigger, then internal temperature difference is lesser. The temperature will not change very easily if the K is very big, right? And vice versa for the external temperature difference, right? Okay. So now I can look at the limiting behavior for different cases. So I already have got this Biot number, and I am again looking at the first term in the equation, the zeroth approximation, let us say, where now I am considering that I am going to get lambda from here. Rather than putting lambda equal to pi by 2, whatever I did, I will get it from here. So what is going to happen when the Biot number is large? When the Biot number is large, then we will have this quantity, which is, I would say, much bigger, or this quantity, the denominator, is going to be very smaller, right? What is the maximum possible value of the numerator? It is Ta minus T0, right? And the denominator will be smallest when my TL is equal to Ta, right? So when the surface temperature TL becomes equal to Ta, that's when the Biot number kind of goes to the maximum possible value, that is infinity, more or less, right? So that is my large limit, and if I plug it in there, Bi goes to infinity, I get lambda goes to infinity, right? And if I plug it in there, my T cap goes to 0. If surface temperature becomes same as ambient, that means my slab is getting cold very fast. So my T cap pretty much goes to 0 in no time. All this I am getting from the zeroth approximation. The actual answer will be approximately same as that, but not exactly same as this, but we are getting the tendencies of the system, right? On the other hand, for a small value of Bi, the denominator has to be bigger and numerator has to be smaller. What is the smallest possible value? When TL is equal to the center line temperature. That means that the slab temperature is not changing significantly. The temperature is same everywhere. And that's the limit when lambda is going to 0, because Bi is equal to 0. If I put lambda equal to 0 here, the time dependence is gone away and we only have the Z dependence. The slab is kind of such that its temperature is not changing with time, right? And that is going to happen, for example, when the Bi is very small. That means my K is very large. So we can go ahead and do it, the full solution for this problem, and do that. But I hope you got the message that the Biot number signifies how effectively we can, or how much time will it take to cool the system, in addition to the time scale that we have defined earlier. Let us now do a different problem, right? In the earlier case, the outside temperature, in the earlier case, the outside temperature was some ambient, but the surface temperature was not same as ambient. So there was like some boundary layer, some temperature variation in the ambient from the surface to the bulk, from the top surface of slab to the bulk, right? But let us say I am doing something like this, that we have a slab that is sandwiched between two hot plates, and the temperature of the hot plates are constant, right? Pretty high temperature or pretty low temperature if we had a cold plate, but we are assuming here a hot plate. So of course the slab must be colder to begin with. So we have a hot plate that is at fixed temperature Th. There is no temperature variation with time in the hot plate. So there is no question of boundary layer, right? So the boundary condition at the top will now change, right? And I will discuss how it will change. And I am interested in the temperature distribution of slab with space and time. So let me now do the heat equation for this problem, and we will start from the very basics. Whatever we have done for the earlier problem, I will do a similar kind of argument, how the conditions will be different for this problem, right? So the very first thing we notice is, do we have center line symmetry, right? So again, if I draw like a center line such that this is my z equal to 0 and this becomes z equal to L and z equal to minus L. Again, since the two plates top and bottom are the same, so therefore TZT is equal to minus T minus ZT. So T is still an even function, and therefore I can use that. And I can again do the 1D approximation, because I can imagine again that the thickness of the slab is much less than the length and the width of the slab. For any slab we can say that, because for any slab the meaning of a slab is like typically that the thickness is much less than the length and width anyway. So I can make those two approximations, but now the other boundary condition is going to change, right? Let me draw this now. My solution domain, we have z equal to 0. I am solving only in z direction. This is my domain. This is my top surface now. In the earlier case, I have equated the heat fluxes, but now temperature of the hot plate is not changing. So instead of that, now I have a boundary condition. The first BC we have already figured out. My dou T by dou Z is equal to 0. This comes from the center line symmetry, that is same, applying same in this case as well. But at the top surface, now I have the condition that T is equal to my temperature of the hot plate, right? So we have still the same heat equation. My initial condition is also same. I am solving for TZT. My initial condition still is some TZ0 is T naught. My first boundary condition is dou T by dou Z at Z equal to 0 is equal to 0. What has changed is only my second boundary condition. My second boundary condition tells me that at Z equal to L, my T is equal to TH. Let me now solve for this case. And again, we can see here that again the condition that we have is not homogeneous. The boundary condition 2 is not homogeneous, so we have to make it homogeneous. And we can again define the dimensionless temperature, dimensionless Z, and so on. Right? Let me do it step by step. So I will define my T cap as something like T minus TH divided by T naught minus TH, and that is same as, by the way, TH minus T by TH minus T naught. Clearly TH is much bigger than T, So the numerator is positive that way, but even if I do this expression, the negative signs will cancel in numerator and denominator. And then I can define this z cap as z by L, and I can again define my small t cap as t by tau, where tau is equal to my rho Cp L square by k. That is simply coming from that equation. That equation has not changed, right? And the dimensionless form is also not changed. So therefore, there is going to be no change in our choice of dimensionless variable, right? Now, let me look at the dimensionless form of the initial and boundary condition, right? So the initial condition, so I have defined my t cap as t minus th by t naught minus th, and I have got my governing equation as something like this. Now let us look at the fate of our initial condition. So in dimensional terms, it is t z0 is equal to t naught, and if I plug it in my definition of t cap, I will get initial condition here as t cap z cap 0 is equal to 1. My first boundary condition, that is my center line boundary condition, is dou t by dou z at z equal to 0 is equal to 0. In dimensionless terms, it is going to be dou t cap by dou z cap at z cap equal to 0 is equal to 0. And my second boundary condition is going to be t at L t is equal to 0, and that is equal to, I'm sorry, th. That's what we have assumed here, right? If I plug it in again this equation, this gives me t cap at z cap equal to 1 and t cap that is equal to 0, right? So pretty much the t cap already is 0 at the top surface, right? And let me now try to solve this equation. Now you see it is homogeneous, and therefore I can now apply the variable separable form. So t cap z cap t cap is some function zeta z cap into theta t cap, and if I plug it in my partial differential equation in dimensionless form, it is something like this. So I again get theta prime t cap, that's derivative with t, into zeta z cap is equal to theta t zeta double prime z, and this I can write as theta prime t cap by theta t cap is equal to zeta double prime z cap by zeta z cap, and that is again equal to minus lambda square, because the temperature is still falling the same way. After a long time, the temperature will be the same as the hot plate temperature. The slab temperature will become equal to Th, and T cap will go to 1. T cap will go to 0, right? So the same thing is happening. T cap is going from 1 to 0. So theta t is decreasing. So theta prime t, that is theta d theta by dt, that is negative, and therefore I have set it equal to minus lambda square, where lambda is a real number. So now I will solve the first PDE. First ODE, that is theta prime t cap, is minus lambda square theta t, and that gives me again theta t is equal to C1 exponential minus lambda square t cap, and the second one gives me and that gives me pretty much the same general solution, C2 cos lambda z prime plus C3 sin lambda z prime. Now let me plug in the boundary conditions that we have got, the first and second boundary condition. So if I plug in the first boundary condition, that is dou t cap by dou z cap at z cap equal to 0 is equal to 0, that gives me zeta prime 0 is equal to 0, and zeta is given as this. So zeta prime z cap is given as C2 lambda with a minus sign sin lambda z cap plus C3 lambda cos lambda z cap, and if I put z cap equal to 0, the first term is going to 0, the second term will remain, and cos of 0 is equal to 1. So C3 lambda is equal to 0. For the same reasons as we have done earlier case, lambda we do not want to set it equal to 0, because if I do that, then my theta prime will go to 0, so temperature will not change, that I don't want with T. So therefore, I will set C3 to be 0. That means I will drop this term, it also gets dropped here. And the second BC is my T cap at Z cap equal to 1 and T cap is equal to 0. This is what I have here, and this gives me zeta of 1 is equal to 0, and zeta of 1, if I look at the expression that I am left with, C3 is already 0, so that gives me C2 cos lambda is equal to 0, and that has a solution lambda n is equal to n plus half pi for n equal to 0, 1, 2, so on. I can still apply the argument of the even function and things like that. So negative n I am going to exclude, and now I have a general solution. Summation of n equal to 0 to infinity a n cos lambda n z cap exponential of minus lambda n square t cap. What has changed from the previous example is how I am evaluating this lambda n, right? So earlier we had an equation like lambda tan lambda is equal to Bi when we equated the heat fluxes, and now we have simply cos lambda equal to 0, and that gives me this. Again, I could have set C2 equal to 0, but that will make T cap effectively 0 everywhere with time. I don't want that, right? So therefore, I will set cos lambda equal to 0. This gives me the value of lambda n, right? And now I can finally apply the initial condition, that is my condition right here, right? And that gives me I will put a small t cap equal to 0, so this will come to 1, and then I can use that to find a n. And just like what I said in the previous example, we will use some orthogonality and all that, but I will not get into how can we derive that, right? So With that, I want to essentially conclude this lecture. In the next lecture, we will take some more examples of heat equation and its analogous equation for diffusion. Right. So with that, I conclude here. Thank you so much.